In this lecture, we're going to cover section 3.3, which is on page 133, and it's about measures of position. So if you look at your book on that page, you're going to see that the first measure of position that is that they are showing is the z-score. So in the last lectures, we learned about measures of center, like the mean, measures of spread or measures of variability, like the standard deviation. Now we're gonna work on measures of position, that they are like measures of ranking, or in this case, we're gonna have, for example, the first one, the z-score is defined on page 134, and there is a formula for that. So the z-score is just a value minus the mean of the population over the standard deviation of the population. So when you do these computations, what you are doing is you are trying to know the number of standard deviations that the value x is far from the center. In this case, the center is the mean. So the number of standard deviations sigma that the value x is far from the center. So, and this score is related to the normal distribution that we're going to cover later in chapter 6. But it's just a curve like this, and the z-score is going to relate the mean of the population and the standard deviation of the population. So if you have a value x here, what you're going to do is that essentially by doing this computation, we are just doing a change of variable. We are just changing coordinates. So you're going to have now what is called the standard normal distribution, where the mean is 0 and the standard deviation is always 1. So now our values are going to be for x, now they're going to be values for z in an interval from negative infinity to positive infinity. So at the end of the day, what we want is to know where the value is with respect to the other values. So measures of positions are just they are giving us an idea where a value is with respect to the other values in the data set. So we're gonna see whether our value is close to the mean or close to the center or far from the mean or from for the center. So the ultimate purpose is trying to know whether a value that we have can be classified as a common or usual value or an unusual. And when you have an unusual value, we say that that value is an outlier. So that's the main purpose of this lecture today on section 3.3, trying to be able to find those values that are maybe not part of the same population, maybe they are coming from a different population. That is going to be one of the main purposes later when we work hypothesis tests or when we try to find confidence intervals for parameters and things like that. But the main tool that we're going to use to do all those computations is uh, being able to compute the z-score. So this is just a formula that we're going to apply, but the important thing is that you know now the meaning, that it's just telling you how many units in the standard normal distribution your value x is from the mean 0. So let's work on the first example corresponding to this section. So the first example corresponding to this section is example 323. This example is on page 134. 134. I'm going to just show you the word problem, and we're going to solve it. So we have here that a National Center for Health Statistics study states that the mean height for adult men in the United States is mu equals 69.4 inches. So they are talking about a population of men, and that's the reason they are giving you mu. So the Greek letter mu is a parameter equals to 69.4 inches. So that's the mean of the population. Then they say with a standard deviation of sigma equals 3.1 inches. So again, they are talking about a parameter of the population. So that's the reason they use the Greek letter sigma for the standard deviation here. So then they say the mean height for adult women is mu equals 63.8 inches. So they are talking about another population. Now, this second population is a population of women. And that population also has a standard deviation of sigma equals 2.8 inches. So now they are asking us who is taller relative to their gender, a man 73 inches tall or a woman 68 inches tall. So we cannot compare apples with oranges, so that's the reason we're going to work uh, two different z-scores, and the z-scores are going to be the way for us to compare things that are different. So we're going to transform the values that are given for the heights to a common scale. Our common scale is going to be the z-score. So that's another way to see the importance of computing the z-score. So let's work on this problem. So we have two populations. I have my population 1 is just adult men, and I have a second population which is about adult women. So I have two populations. Now I have also parameters. So parameters are just numerical values describing the population. So we have parameters for our first population. We have mu is going to be 69.4 inches, and a standard deviation equals 3.1 inches. So these two values are describing a population, the population of adult men. Now we have two more values describing the second population, and those values are the mean is going to be equal to 63.8 inches, and the standard deviation is going to be 2.8 inches. So now we have our two populations described. So now we have two individuals. So we have one individual, one man, with height equals to 73 inches, and I have a woman. Let's say I'm going to call this Y. Her height is 68 inches. So I have two individuals. So if you compare these two individuals, you're going to say, oh, the man is taller than the woman. But that's not the right way to do this comparison. So you need to compare men with men and women with women. So that's the reason we're going to use the z-score. The z-score for this man is going to be just x minus mu over the standard deviation. So we're going to get, and be sure that you use parentheses when you word these differences to prevent mistakes. So it's going to be 73 minus the mean, which is 69.4 over the standard deviation 3.1. So we're going to find a value for that man in a minute. So now for the woman we have another z-score, and this is going to be y minus mu over sigma. And I can say this is the z for x, the z for x, the z for x, and this is the z for y. The z for the woman y is going to be 68 inches, don't forget the parentheses, minus the corresponding mean, which is 633.8 over the standard deviation 2.8. So now we're going to get two values, two z-scores that we can now say something about those two z-scores. So let's work on this by using our R console. You can use just a regular and ordinary calculator. So I'm going to do just the difference, 73 minus 69.4, and don't forget this parenthesis, divided by 3.1. So I get my first z-score. So this is 1.16, 129. Then for the woman, I have 68 minus 63.8 over 2.8. So this is going to be 1.5, 1.50. So that's those are the z-scores for these two individuals from coming from two different populations. So now we can say something about this. So who is taller? So we're gonna say we're gonna write our response. So and we can use some figures to understand this better. So we have what we have is that we have the population 1. So these are men heights, adult men heights, and then so adult. And then we have another population, which is adult women heights. So the heights are is what the populations are consisted of. So then we have again the mean for each population when you use this course is always 0, and then you only need to write where the z-score was or is the one that you found. So for men we found a z-score of 1.16. So and this is for a value of height equals 73 inches, and for the woman we found a z-score 1.50. So our z-score is 1.50, and that is for a height equals to 68 inches. So now we can see that this woman's height is farther from the mean than the height of this man. So we can say that the woman with height 68 inches is taller than the man with height 73 inches with respect to their corresponding populations. So that's the purpose of finding these scores. So in your book you're gonna get some empirical rules. So we have these scores and the empirical rules. So again, looking at these curves, remember this is the standard normal distribution. So we wanna know about this in a better way when we cover chapter 6. But in general terms, we can say that you have the mean here, and for example, we can have values 1, 2, and 3, -1, -2, and -3 for the z-scores. So when you have these z-scores, what you're gonna say is that between -1 and 1, between these two values, you're gonna find 68% of the data. So 68% of the data is gonna be between these two values, -1 and 1. Between -2 and 2, we're gonna find 95% of the data. And finally, between -3 and +3, you're gonna find almost all the data, almost all. So something like 90.9% of the data is gonna be between -3 and +3. So the importance of having these scores is that you're gonna be able to determine whether a value that you find, an x, given an x, and you find your corresponding z, you're gonna see, or you're gonna say whether that value, the original value, is an outlier or not. So outliers are going to be values with z-scores out of the interval -2, +2. So in other words, if I have +2 here, -2 here, everything out of this interval is going to be considered an outlier. So this is the region for outliers. These regions here, these are the regions for outliers. So everything in between can be considered a normal value or usual value. So again, anything out of the 95% of the data, so this 5% that remains is going to contain the outliers. So now you're going to work some exercises from the exercise set. I'm going to give you a break, and then we're going to continue with more measures of position, measures of ranking. Okay, so we have section 3.3 on page 146. We have an exercise set there, and you're going to solve problems 17 and 18. So let me project the corresponding work problems, so for you to start working on those problems 17 and 18. Okay, so we have 17 here and 18. Okay, 17 and 18. A population has a mean, mu equals 7, and a standard deviation sigma equals 2, and you're going to find the z-score for a population value of 5, then another z-score for a population value of 10, and then you're going to do the opposite. You are given the z-score and now find the corresponding value x, and the same thing with the problem 18. So first you are given a value of x, for example 16 in problem 18 part A, and you're going to find the z-score. In part B, you are given x equals 31, and you need to find the corresponding z-score. And finally, the opposite, you are given z-score, a z-score equals 2.5, then you need to find the corresponding value for x. So you're going to need to use then this equation. So given x, to find given x, you just find z by using this formula. Don't forget the parentheses. And the other case that you are having in these two problems is that when you are given z, then you're going to find x. x is going to be mu plus z sigma. So you just solve for x here. So you need to multiply by sigma both sides of the equation, and then you're going to move this to the left hand side. So you're going to get mu plus z sigma. So these are the two possible cases that you're going to have in these two problems. So we're on this, and then we're going to return to continue with the next part of the section. So now we're going to compute quartiles. That's another measure of position. And actually, measures of position are like measures of partition. So we're going to subdivide the data set in parts. So for example, when we computed the median in the last section, what we did was we ordered the values in ascending order, and we look for the value in the middle. So in other words, we were breaking or partitioning the data set into equal parts. Now with quartiles, we're gonna partition the data set in 4 parts. So, and we're gonna have a first quartile for the first quarter, then for the first quarter, and then we're gonna have the second quartile, which is half of the data set, which is the median. And finally, we're going to have a third quartile, which is going to be the 3/4 of the data set at that location. But for example, we have here a table with annual rainfall in Los Angeles during February. So in order for us to get the quartiles, we're going to need to put these values in order. So let's let me just show you a summary of the work that we're going to do now with quartiles. So quartiles are described on page 135. And we have the first quartile. As I mentioned before, it's going to separate the lowest 25% of the data from the highest 75%. Then we have a second quartile, which is the median, because the median separates the lower 50% of the data from the upper 50%. And then we have a third quartile. That quartile is going to separate the lowest 75% of the data from the highest 25%. So as I mentioned before, it's like having 1/4, 1/2, and 3/4 of the data set. So to compute the quartiles, we only need to follow a recipe. So the recipe is on page 136. We're going to arrange the data in increasing order, as we did with the median. Then we're going to find quartile 1 in the location that's going to obtain with the formula that is here. So L is going to be equal to 0.25 n, where n is the number of data values. So we're going to use 0.25 because this is 1/4 of the data set. And Q3, the third quartile, is going to be the value that we're going to find at this location, 75% of the number of data values, so 0.75 times n. So to be a little bit more consistent with other computations that you find in other textbooks, we're going to take into account the following notes. So if L, the value that we're going to find after applying this formula, is a whole number, then the quartile that we're going to find is going to be the average of the numbers of the values in positions L and L plus 1, so 2 consecutive positions. We're going to get the values for those positions, and we're going to get the average, and that is going to be the value for the quartile that we're looking for, either Q1, Q2, or Q3. But this is only in the case that L results to be a whole number. Most of the time it's going to be a non-whole number, so it's going to be just a whole part with a decimal part. So you're going to need to round up, and then the quartile is going to be the number in the position of the rounded L. So you're going to look at the table, the order table, and look for the value that is in such a position. So we're going to solve a problem just to see the recipe in action. So we have example 324 on page 136, and this is going to be just, we're going to compute the first and third quartiles of the Los Angeles rainfall data, of the Los Angeles rainfall data. So it's the table that I showed you before, but now first we need to count the number of data values. So if we count the number of data values, we're going to find that there are 45 data values in that table. So the next step, we need to order the table. So table 3.9 should be ordered. You can use sort of X to order your list of values. And if you do that, you're going to get table 3.10. So this is using an R command in our console. So you're going to see now the table 3.10, the one that is going to have the data set in increasing order of values of the rainfall. So you have here the data set. So now you can see that the rainfall starts with the minimum value 0, and then start increasing 0.08, 0.13, 14, and so on until we get the maximum value of rainfall, which is 13.68. So now that we have these values in increasing order, now we're going to be able to find the positions of the locations for the first quartile and the third quartile. It's like partitioning this table in 4 parts. So we need to find the boundaries, dividing the first quart from the second quart, and so on. So let's do that. So what we're going to do is we're going to find, for the first quartile, we're going to find the location. So the location, so for the first quartile, we need to find the location first. So the location is just 0.25 times n. So in this case is 0.25 times 45. So if we use a simple calculator, we find 11.25. So this is not a whole number, it has an integer part and a decimal part. So we need to round up, and it's going to be 12. So this is the location where you're going to find a value. The value that you find in this location, in this position, is going to be your first quartile. So let me just finish by finding the third quartile. So the location for that third quartile is going to be found by multiplying the number of values by 0.75. So if you do these computations, we're going to get 33.75, and then we're going to round up. So we're going to get 34. So this is another location, the location. So this is for the third quartile, and this is going to be for the first quartile. So then we need to go back and count the position 12 and the position 34. So let's do that. So we have here our data set. So we find position 12. So it's going to be 1, 2, 3, 9, 10, 11, 12. So this is the position 12. Is 0.83, the value that is there. So we're going to write here Q1 is going to be 0.83. Okay, again, this is in the 12th position in the order data set. Okay, now let's do the same thing with the other value. We need to look for the 34th position. So we will go back here. So there are 9. 3 times 9 is 27. So this is going to be 28, 29, 30, 31st, 32nd, 33rd, and 34. Is that the one that we are looking for? The 34 location is 489. So this is going to be my third quartile. So I'm going to write here that my third quartile is going to be 4.89 because it's in the 34th position in the order data set. Because if you don't order the data set, the values that you're going to get are going to be completely different. So this is the section about, or the part about quartiles. Now we're going to work on a more general measure of position or measure of partition, which is going to be percentiles. Percentiles is a generalization of quartiles. So now instead of looking for the 25% of the data set or the 75% of the data set, we're going to look for any percentages for any part of the data set. So this is going to be now, I'm going to work now on percentiles on page percentiles. Percentiles are described on page 137. So there is a definition there. We're going to copy the definition in a minute for our notes. So this definition is the following. It says that for a number p between 1 and 99, the pth percentile separates the lowest p% of the data from the highest 100 minus p%. So that's the definition. So we're going to write this down. We need this information in our notes. So we're going to say that for a number p between 1 and 99, comma, the pth percentile separates the lowest p% of the data from the highest 100 minus p%. So for example, we might have some percentiles. So let's say the 25th percentile separates the lowest 25, this is P, 25% of the data from the highest, and then we do 100 minus P. 100 minus 25 is going to be 75%. So, and what is this 25th percentile? This is Q1, right? And we have a similar definition now in terms of percentiles for the third percentile and for the second percentile. So for example, the second one, the 50th percentile is going to separate the lowest 50% of the data from the highest 50%, because 100 minus 50 is also 50. What is this? This is Q2, the second quartile, and it's also the median. So that's the median. So finally, the 75th percentile, you're gonna see that this again is gonna be the same thing. The 75th percentile is gonna separate the 75% of the data from the highest 25%. So this is gonna be the third percentile. So what is the procedure? The procedure is very similar to the one that we just wrote for quartiles. So what is the procedure? Procedure for this is going to be for computing the data value corresponding to a given percentile, corresponding to a given percentile. So this is on page 138. So what are the steps? Are the same as before. We're going to arrange the data in increasing order. We're going to arrange the data in increasing order. Then we're going to compute the location. So we're going to find the location L as P times N over 100. And we have the same rules as before. So if L is a whole number, then the percentile is going to be L, the value at L. So let's say that is X at L plus the value at L plus 1, and we're going to divide this by 2. So this is going to be the percentile. The percentile is going to be XL plus XL plus 1 over 2. But if L is not a whole number, then the pth percentile is going to be just the value at the L value that is rounded up. So you're going to look for the L that is rounded up, and you're going to find the corresponding value. So let's work an example, and then we're going to do the opposite. Sometimes we want to know the value that corresponds to a given, we want to know the percentile corresponding to a given value. So let's solve example 3.26. So this example is based on the same table. So we're going to compute the 60th percentile of the Los Angeles rainfall data. So we have again the table that I showed you before with the rainfall data order in increasing order. So we're gonna first first we arrange the data in increasing order. That's table what is the table? Let me see. Okay, that table is table 3.10. So you look at that table, it's already in order. So page 136. So that's the first step. If you don't have order, if you don't have your data set order, again you need to enter X, all the values, and then you're gonna do sort of X, and then you're gonna get the list order. So the second step is just gonna find the location. So in this case, the location is just P times N over 100. So P is 60 times the number of data values. We know that there are 45 data values, and we're going to divide by 100. So if you do that, we're going to get 27. So now 27 is a whole number. So the 68th percentile is going to be the value in the position 27 plus the value in the position 28, and we're going to divide those values by 2. So we need to find the position 27 and 28. So 27 and 28. So let's check the table. So we have the table here. So position 27. So this is 9, 18, 27 is 3.57, and the next one is 3.58. So we're going to combine these two values and divide by 2, and that is going to be the 60th percentile. So let's do that. To finish this problem, we're going to write let's decrease the size of the font. So we have our 60th percentile is the value in the position 27. We said that is 3.57 plus the value in the position 28. That is going to be 3.58, and we're going to divide that value by 2. So if we do that, we're going to get 3.575. So that's the value that separates 60%, the lowest 60% of the data. So if you have the data set in order, this is the entire data set. This is the rainfall data. So, and this is 60th percentile. So we have 60% of the data here, and we have 40% of the data here. Then the value that separates this list into parts, this value is 3.575. So that's the meaning of computing a percentile. So now we're gonna do the opposite. So now we're gonna have given a value x, now we're gonna find the percentile. Okay, so now we are going to have x, and we want to know that value, how that value is dividing the data set, how that value is partitioning the data set, what percent is on the left of that value, and what percent is on the right of that value. So the procedure is on page, the procedure for computing the percentile corresponding to a given data value is going to be first, again, we need the data in increasing order. So we arrange the data in increasing order. So this procedure is on page 138. Then we're going to use a formula now. So the percentile corresponding to that value is going to be 100 times the number of values less than x, number of values less than x, and then we're going to add 0.5 to that value, and then we're going to divide by the total number of values. So the total number of values in the data set. So that is going to be the formula. So we're going to work now example 327 on page 138. So the problem says that in 1989 the rainfall in LA during February was 1.90. So the question is, what percentile does this value correspond to? Okay, so we want to know where is this value in relationship with the other values in the data set. What is its position? So again, we're going to use table 3.10. Is already ordered, otherwise you need to enter your data set, and then you're going to use sort of x to have your list order. So now we're going to do the next thing, which is just getting the percentile. It's going to be just 100, and we're going to count the number of values that are less than 1.90. So we need a table 3.10. So let's see, we have our table in order. So we need to count the number of values that are less than 1.90. So we need to find 1.90 is here. It corresponds to 1989, as they say. So we count the values that are less than 1.90. So there are these 9 values and these 9 values. So in total 18 values that are less than 1.90. So we're going to write here 18 values plus 0.5, and we're going to divide that by the total number of values. So what is this percentile then? We do the computation by using our calculator or by using R, it's up to you. And you're going to get 41.1. So we can round this off. So we're going to get the 41st percentile. 41st percentile is the one that corresponds to 190. Okay, so we can say the 41st percentile is 1.90. Okay, so I think now you should be able to solve some problems in percentiles, and then we're gonna end up with the final part of the section. So let's see. You're gonna work section 3.3. As I said, on page 148, you're gonna work problem 32. Only one problem. Problem 32. That's what you're gonna do. So let me look for the problem for you. So 148. So we have here problem 32. Okay, problem 32. You have a data set. Remember, you're gonna need to sort out this data set. Problem 32 is about cholesterol levels. So you have 40 values there, and you're going to respond these questions. You're going to find the first and third quartiles. You're going to find the median, and you're going to need to find also only that one, the median, the first quartile, the third quartile. So you're going to solve part A, part B, and then you're going to solve part G and part H. The rest, you need the last part of the section that I'm going to talk about in a minute. So solve part A, B, G, and H for this problem. So now we're gonna collect all the most important values, the measures of position that we have studied today. So, and we're gonna define a 5-number summary. It's on page 139, and that 5-number summary is just the collection of the minimum value, the first quartile, the second quartile, which is the median, the third quartile, and the maximum value. So these 5 values are values that are important to see how a data set is distributed. So you can also get those values if you just, again, define your variable x as a collection of values, and you enumerate all the individual values, and then you use the command summary of x. You're going to get 6 numbers instead of 5, but the extra number is going to be just the mean. So you're going to have, in addition to these 5 numbers, you're going to get also the mean. So the purpose of getting these 5 values, is because we're going to use those values to identify values that are unusual. So those values that are unusual in a data set are called outliers. The definition is in page 140. An outlier is a value that is considerably larger or considerably smaller than most of the values in a data set. So in other words, it's an unusual value. It's a rare value in the data set. So to be more precise on finding these outliers, we're going to need to compute a couple of more numerical values. For example, the interquartile range is going to be the difference between the first and the third quartile. So it's Iqr is going to be Q3 minus Q1. So we're going to use that in the method that is called the Iqr method for finding finding outliers. So this method is to find outliers, and this is defined on page 141. So the first step is going to be finding the first and the third quartile. We know how to do that. Then we're going to compute the interquartile range, which is just the difference of these two values. And then we're going to compute boundaries that are going to determine the region where you're going to find the outliers, and it's going to be distinguishable for the region that is just the more ordinary or common values for your data set. So the lower limit is going to be the lower outlier boundary. Is computed by subtracting 1.5 times the interquartile range from the first quartile, and the upper limit, or the upper outlier boundary, is going to be obtained by adding 1.5 times the interquartile range to the third quartile. Then the values that are outside of this interval, when you have the lower and the upper limit, values that are outside of this interval are going to be outliers. We're going to have a final tool, a graphical tool, to visualize outliers, and it's going to be the box plot. A box plot is going to be then a tool that we're going to use to visualize a data set, and also to see the outliers in the data set. So the steps are very similar to the previous steps I just mentioned. Now we're going to incorporate, use the graphical part. But we're going to start computing the third quartiles, Q1, Q2, and Q3. Remember, Q2 is the median. Then we're going to draw vertical lines at Q1, Q2, and Q3. And then we're going to draw horizontal lines between Q1 and Q3 to complete a box. Then the next thing is we need to compute the lower and the upper limits for the region that is going to distinguish the outlier regions from the middle region, which is going to be the region with the more ordinary values. And then when you have those values, the lower and the upper outlier boundaries, we need to find the values that are closest to these boundaries but inside of the interval, and we're going to draw a horizontal line for those values to the next or to the nearest quartile. So, and your book says that these lines are going to be the whiskers, so check page 142 to understand this better. Finally, we're going to find and plot the outliers. So I'm going to solve example 3.32 on page 142 to see just the steps to build a box plot. So this example is about constructing a box plot for the absence data, for the absence data in table 3.11. So now we have a different table, we have a different data set. So that table is, let me see, where is that table? 3.11. So it should be here. So we have here the table. So 3.11 is here. So this is the number of students absent in a middle school in Montana. And this is a table with the date and the number of absences that they registered, they recorded. So January 2nd, 65 students didn't attend, and so on. So we have the values that are of interest for us is the column that record the number of absence, that records the number of absences. So it's this column, and this, and this. So we're gonna enter these values into R because we need to order these values to find the first quartile, the median, and the third quartile. And we're going to use now the summary command to do this in a fastest way. So we're going to then go and check on R how to do this. So let's see, we have R here. So I have here now my data set from table 3.11. So we have X equals the first number of absences is 65 and 67, 71. So 71. So you have a long line here of values. If you want to see the rest of the line, because you see here a dollar symbol, meaning that there is more on the right. So I can continue scrolling to the right, and you can see all the data sets up to 51, which is the last value. So then, if you want to find the first and the third quartile by hand, then you need to sort the data values. I sort in here by using sort of X. So I know I have the values in order, in increasing order. But you can do this after. I'm just going to use summary of X to get the 5 numbers and the extra one. So I have the minimum value now. I'm going to write this in my notes. So I have the minimum is 41. Then the first quartile is 45. Then I have the median, which is the second quartile, is 51. Then I have the mean. I don't need the mean in my for my box plot, so I'm going to write the third quartile, which is 59. And finally, the maximum value is going to be 100. So those are the values that I'm going to use to draw my box plot. So let's go back to our notes and continue with our work. So now I have my phi. This is the phi number summary. So I have the 5 values that I need to build the box plot. So let's start. So we can see here, the step 1 is just we need Q1, Q2, and Q3. So we have Q1 equals 45, Q2 equals 51, and Q3 equals 59, 51 and 59. So then the next step is we're gonna draw vertical lines. So we're gonna start drawing our so let's do that around here. So I have a number line, that goes from approximately 40, because 41 is the minimum value and 100 is the maximum value. So I need to divide this in parts. So I'm going to have here is going to be 70, then in 3 more parts here, let's say 80, 90, 50, 60. You can do this very using a grid paper. So then I need to draw vertical lines. I'm going to use a pencil at 45, which is the first quartile. So around here, vertical line, another at 51, and another one at 59. So I have my vertical lines there. Then I need to draw horizontal lines to complete the box from Q1 and Q. So this is Q1 and this is Q3. So I have my horizontal lines. So now I can use my pen. So I'm going to do this thing. So if you check the figure in the book, it's better. Then we need to compute the outlier boundaries. So that's the second part. We need the outlier boundaries. So we need the lower outlier boundary and the upper outlier boundary. So for that we need the interquartile range, which is just Q3 minus Q1, so 59 minus 45. So this is gonna be 14. So then the lower interquartile is 45, the first quartile, minus 1.5 times 14, and in the other case the upper quartile is going to be 59 plus 1.5 times 14. So we do these computations and we're going to get 24 and we're going to get 80. So we're going to draw another vertical line at 24. So it's out of the figure, and 80. Okay, so 24 is around here. But we need to look for the values, the closest values to these two boundaries, but that are inside of this interval. So what are those values? We need to check our list of values. So we need to look the sorted list. So we go back to R, and we're gonna find those values. So I have the sorted list. So I have 24 is my lowest or my lower outlier boundary, 24. So I need a value that is greater than 24 in my list, and it is 41. So 41 is the value that is, I'm going to draw a dot. 41 is the value that is closest to that lower outlier boundary. Now my upper outlier boundary is at 80, so I'm going to move this. I have 77 and 100. 80 is in between, so the closest value to 80 is 77, and 77 is inside of the interval, so I'm going to look for 77. So I'm going to do another point there. So that's what I need for this data set that is sorted. So I just found two values. 41 is here, 77 is here. So this value is on the left of the upper boundary, and this value is on the right of the lower boundary. And then you just draw horizontal lines from the corresponding points to the nearest quartile. So that's what we do. So this is the nearest quartile is here for this one, and the nearest quartile for this one is here. And they call these lines whiskers. So that's almost done. So we need to start now plotting the outliers. So you go back to the list and look for the values that are less than 41 and greater than 77. And we saw that there is only one value that is outside of this region, which is 100. So you're going to use a mark for that outlier. So that's our box plot now. So now you're going to be able to solve a couple of problems in which you're going to do the entire thing. So until you get a box plot. Okay, so you're going to work 3.3 section 3.3 SSI set, and this is on page what page is this? So this is gonna be okay. We have this problem on page 148. So you're gonna finish problem 32. Now you are able to work on all parts of problem 32, and also you're gonna work problem 36. So I'm going to show you again problem 32, and then I'm going to show you problem 36, and with that we're going to finish this lecture. So I have here problem 32. So now you need to complete the entire exercise. So you just found before the first and the third quartile for this problem. Then you found also the median. Now you need to find the upper and the lower outlier boundaries and look for outliers. If there are outliers, you're going to create a list. Then you're going to construct a box plot for this data, and then you're going to describe the shape of this distribution. Finally, you already computed G and H, the 20th percentile and the 67th percentile, and you only need to incorporate one more problem. One woman had a cholesterol level of 58. You need to find the percentile given a data value. So that's problem 32. Problem 36 is here. It's about a nuclear power plants or reactors. So it's a table presenting nuclear reactors in a recent year per country. So you're going to need this table. You need to order the values on the second and the fourth column, number of reactors. Once you order those values, then you're going to respond the questions similar to the previous ones. So finding quartiles, outlier boundaries, finding outliers, constructing a box plot, and also talking about or finding percentiles and values given percentiles. So that's all for this lecture today. So send your data results to our classwork section, so by using the submit button, and then we're going to continue the next time.